Hi everyone, welcome to Chapter 9, which is about the hydrosphere and water resources. So far we've talked about the water in the atmosphere, and now we are going to talk about the water everywhere else, which will pretty much sum up our kind of water systems in this chapter, although we will talk about water a lot later when we talk about erosion. Near the end of the semester, we'll talk about glaciers, which obviously is another type of water, but most of the water we're going to cover in this chapter, Chapter 9. So a quick review, we talked about how most of the water on the planet is salt water. There's only a very small portion that is fresh water, 2.5%. Of that 2.5%, glaciers take up a huge amount, permafrost a little bit. Remember that atmospheric and surface water takes up 0.4% of that 2.5%. So that surface and atmospheric water, that includes all of our lakes, right? All of our readily available freshwater, lakes, rivers, wetlands, also moisture in soil. Groundwater, which we're going to talk about in the second part of this lecture, makes up about 30% of this freshwater, which is an important water source, especially in Southern California. And when we look at our water withdrawal from groundwater, we use a huge portion of it for agricultural demand, a little bit for industrial manufacturing, and only 10% for domestic. And this is important to remember because when we talk about water conservation at an individual level in our households, it's very, very important. But we also want to remember that most of the water we are using is for agriculture and then followed by industrial purposes. We've gotten really good in Southern California at saving water for the most part. There's always room for improvement, but we've come a really long way. So more review again. Remember, this is our hydrologic cycle, which I mentioned briefly. So you have precipitation that falls. It flows on the surface and below ground as well. Will run down to the ocean or larger bodyways. You'll have evaporation that comes up. You'll get condensation, more precipitation. We also get something called evaporation and transpiration, which is also can be referred to as evapotranspiration. So plants and vegetation also will let off a certain amount of water with evaporation when you water them. So a huge portion of the water on our planet, obviously, is our oceans. It's really one gigantic connected ocean. We do have some salty bodies of water that are in endorheic basins, which we'll talk about a little bit later in this lecture. But generally speaking, all of our oceans, one big connected ocean. The designations for us are just for us, but the Indian Ocean and the Atlantic Ocean, the Pacific Ocean, and the Arctic Ocean, they're all connected. Right? So it's interconnected. It's one big ocean. It's all salty. The reason that it's all salty is because as it rains and as that water runs over land, it picks up minerals and salts. It deposits them into the ocean. And then when evaporation happens, those salts are not evaporating. So the salt is staying in that ocean. The oceans are the endpoint for most rivers. Some flow into endorheic basins, and again, we'll talk about endorheic basins in a minute, but it is that endpoint for most rivers. And so those minerals accumulate, and that's why our oceans are salty, which is good for all the wildlife that lives there, not really good for us for drinking, and we'll talk about desalination a little bit later in this chapter. So something else important to remember, waves, right, which we're very familiar with in Southern California. Waves are just basically a flow of energy. So it is kind of the water's response to wind. Tides are basically the pull from lunar gravity. And so what you have here is you get a high tide on either side of the planet here. So you have the moon, its gravitational pull is pulling the water from the sides of the planet. And then this water over here is also high tide because it's not being pulled like this on the sides. So important to remember, our tides are caused by a pull from lunar gravity. So it depends on where the moon is. They affect local circulation of water only, right? They don't push water around globally. Currents, though, are these kind of big surface conveyors of water, and they move heat and nutrients. And so we have some big currents. We have uh, shallow water currents and deep water currents, but we have these flows of water that consistently travel through our oceans in somewhat predictable patterns. And so if you've watched Finding Nemo or more recently Finding Dory, right, they need to hitch a ride on a certain current. Uh, so beyond our oceans, we're going to talk about our surface water, right? And so this includes streams and lakes. Most of this water eventually will run off into the oceans. And these places are connected by groundwater. What we don't see or what we often think about is the bottom of a lake or a river is a permeable surface, which means water can seep through it. And so there's an entire groundwater system of flowing water that's happening. And so in the second part of this chapter, we're going to talk a lot about groundwater. The other thing that's important to know is that we have erected thousands of dams. Most of the major rivers in the world, and especially in this country, have already been dammed up. And so a dam is any obstruction placed in a river or stream to block the flow of water. We do this for a couple reasons. We do it to prevent floods, provide drinking water, allow irrigation for farming, and also generate electricity. And so in my hometown in Connecticut, we had a reservoir that provided the drinking water for my town and a few adjacent towns. It was a very local water source. We have 45,000 large dams have been erected in more than 140 nations. They were very, very, very popular, especially it was seen as this big infrastructure project. You can think about kind of if you've been to the Hoover Dam, what a massive project that is. There's only a few major rivers that remain undammed in remote regions of Canada, Alaska, Russia, and Africa, but most of the major rivers in the world have been dammed. China's Three Gorges Dam is the largest in the world. It has a 385-mile long reservoir behind it. And so you can see here is the Three Gorges River in 1987 before it was dammed. Once you erect a dam, this area behind it floods, and so this becomes your reservoir. And so there were people who were living here who were removed. One of the benefits of having a communist regime is that you could just tell people, oh, you're moving now. In the US, it happens a little bit differently. But we're not really constructing new dams in the U.S. We're mostly removing them. And so we have also dammed the Nile in Egypt, which has resulted in kind of more water being available upstream and less downstream. You're going to look at in satellite imagery of that Nile River Valley after you watch this lecture, and you're going to see just how important and how compact life is in Egypt around the Nile. Everybody really lives right near the Nile. And then again, I mentioned previously the Hoover Dam, which if you're ever in Vegas, it's a short trip to go see the Hoover Dam, and it is really quite massive and impressive to see, and provides a decent amount of hydroelectric power. So when we dam rivers, that water backs up behind it, that reservoir is created. And that can generate electricity. As they're letting water kind of flow slowly through that dam, it's turning turbines and it's generating electricity. It can also aid in flood control. So you can prevent, if you have a lot of rain upstream, you can prevent a certain amount of rain from reaching downstream and potentially flooding areas. So some dams are being removed. So some people feel that the costs of dams outweigh their benefits. And when you let rivers flow free, you can restore ecosystems, you can reestablish economically viable fisheries, and revive river recreation, specifically fishing and rafting or kayaking. There are a lot of Native American tribes, especially in the Northeast, who typically fished salmon upstream in rivers, but those salmon populations have disappeared because they can no longer get upriver. Some dams will have kind of fish bypasses to try to help with that. So old dams or those that are no longer economical are good candidates for removal. One of those is the Condit Dam. After this lecture, you're going to watch a video of this dam being removed. Actually, you watch it kind of explode. It is not as dramatic as it sounds, though I think it's pretty cool. And all of this water flowing past it and kind of what it looks like after. This was a few years ago. A lot of it has revegetated now. But you wind up, what happens behind a dam is all of that sediment that would normally be flowing down a river is now stuck behind that dam. And so when before they removed the Condit Dam, they had to let all the water out, but then they also had to remove quite a bit of sediment. But pay attention when they blow that dam. That is, very brown, silt-filled water that is coming down. So you can't. It's not just as simple as taking the dam down. You've backed up a lot of sediment, which also affects ecosystems downstream because you're no longer kind of replenishing floodplains with this sediment. And so there's been problems. So right here is behind the Condit Dam, or what used to be the Condit Dam, the water used to go up to here. And so you have houses right here that were basically lakefront property. And now the groundwater that was in here too has also dropped. So people's houses are starting to sink here. And so this is a picture of a woman in her house whose the foundation is cracking, the ceilings are cracking due to the fact that you've removed that water that was holding up that ground. Next, we're going to talk about lakes. Lakes are created in many different ways, but they are a place in a drainage system where basically water accumulates, right? They are some type of depression, and so like a bowl, if water is flowing into it, it's going to accumulate. Most of them are drained by rivers. So if you look at here, the Great Lakes, you can see these blue lines. There are actually rivers that are connecting all of these lakes. So they are being drained. And this removes the minerals. So like I said before, when you have rivers that their endpoint is the ocean, they're carrying a lot of minerals down there and they're depositing them there because there's nothing to remove them. But that's why we have freshwater lakes, because those rivers are removing those minerals and eventually depositing them to the ocean. Some of them do not drain though, and those are called endorheic lakes, and they exist in endorheic basins. So the Great Salt Lake right here is an example of one. And so basically rivers are flowing into them. They will eventually dry up as those river systems leave, but basically those minerals are accumulating in there, and so you wind up with a Great Salt Lake because there is no way for it to exit. And so those bodies of water will get saltier and saltier. Here you can see where the Great Salt Lake also used to be, and so now there's just these big salt flats where nothing can grow because it's just so salty. So they are like mini little oceans that get saltier and saltier over time. The Salton Sea, which you watched something about, that is in an endorheic basin. So there's no exit point for that water, and that water is just getting saltier and saltier and saltier until most wildlife can no longer live in it. So lakes don't last. They're there for a while. Most of them are there longer than we kind of notice in our lifetime. We're talking about very long periods of time, but some do disappear within our lifetimes. They fill up with sediment. So basically you had that bowl, but a bunch of sediment is flowing in there and it fills it up. So there's no longer kind of a basin there, that bowl shape to hold that water anymore. Some of them lose their source of water. Either a river kind of naturally chooses a different path, or we can reroute that water, which I'll show an example of the Aral Sea. And here is it on a map, and here's a picture of it in Central Asia. And this can happen really, really quickly if a lake loses its source of water, especially if it's in some place that's very warm and does not get a lot of precipitation to kind of help with that replenishment. And so here is an historic map of the Aral Sea, which was in an endorheic basin and was very, very large. So large endorheic lake. And again, endorheic means that it does not have any way to drain the water and sediments from it. It's in a very dry climate zone, so not a lot of precipitation that's happening there. The rivers that fed the lake were primarily fed by mountain snowmelt that was happening in another place and then flowing down. In the 1960s, the rivers were used for irrigation, so a lot of water was being taken out of those rivers in order to irrigate to grow cotton. If you know anything about cotton, it's an extremely water intensive crop. So lots and lots of water are being used for this cash crop of cotton. And so the lake began to shrink quite dramatically. And also, as that lake was shrinking, that salt content was rising because there was less water to kind of dilute that salt content that was in there. And so, just to give you an idea of how big the Aral Sea was historically, so here is a map of San Diego, LA. This is it laid on top of it for size. So, it's really, really large body of water, very important in the region. And so, you can watch as this shrinks pretty dramatically after 2000. So there's very, very little left now. This part is all dried up. And so what's left is these two little parts, which people are kind of trying to hold on to. Here you can see the line of the historic. This is from when we have good satellite imagery, just to show you. And so you wind up with scenes like this, fishing communities that were just completely devastated by this, and obviously a big problem. And so there is what it looked like as of 2014. It looks pretty similar now. And again, they're trying to save these little parts of it, but just a huge body of water that disappeared. That is the end of the first part of this, of the Chapter 9 lecture. When you come back for the second part of Chapter 9, we're going to pick up talking about groundwater.